Hey guys, Mr. Betts here. I want to talk a little bit about the connection between differentiability and continuity. So, differentiability, as you might guess, is the ability to differentiate a function. So, differentiating a function is taking the derivative of the function. So, if a function is differentiable, then we can take the derivative of it. We've also talked quite a bit about continuity, and we formally define continuity using limits, although the kind of informal intuition of continuity as being able to draw a function without lifting up your pencil is going to work well enough for making this connection. So the question that I want to answer is, what features of the graph of a function would cause the derivative to not exist? And to answer this question, I'm gonna use a couple of things here. So first of all, let's remember that the derivative of a function is defined as this limit. So this is the derivative of a function at a particular point. So when we're talking about differentiability, we're going to look at individual particular points and say the function is differentiable or not at those points. So this is one definition of the derivative at a point. Remember, there's another one where we had the limit as h approaches 0 of f of x plus h minus f of x over h. So this is actually the x's should be replaced with c's here for this example. So this is the derivative of f at c also. It doesn't matter which one of these limits that we use. The important thing to understand here is that the derivative is defined as a limit, and for this limit to exist, the two-sided limit has to exist. So this has to be true whether x is approaching c from the right side or x is approaching c from the left side. And that's going to be important here in our discussion. So the other thing I'm going to use here is a graph of a function that has some continuity issues to it. So there's going to be a few things that's going to cause differentiability issues, and some are related to continuity. So I'm gonna go through our piecewise function here, kind of one piece at a time, or at least one part at a time, and talk about whether a function is differentiable or not at particular points and why. So I'm going to start with just kind of a boring point here, the point at x equals -2. At this point, remember the derivative is the slope of the tangent line at that point. And if we look at a tangent line to a line, the tangent line and the line are going to be the same thing, and we have no problems. Okay, so no problems with the derivative at a point on a line or even a smooth curve. So anywhere between -1 and 0 here, we're going to be able to take the derivative. Where we might run into trouble is at these points of discontinuity. So let's look at -1 here. So if c is -1, then we're looking at this limit as x approaches -1 from the left, and the limit as x approaches -1 from the right. So f of c and c are going to be, in this case, at -1, f of c is going to be -1. I'm sorry, f of -1, which is 2, and c is going to be -1. So that's not going to change. What is going to change is the values of x that are approaching 1. And it's important to understand here that they're going to be different depending on if we're approaching from the left or from the right. So if we're approaching this point from the left, then we're going to be getting points that are really close to it here. We're going to be getting slopes that are matching that line going off to the left. What's going to be troublesome here is as we're approaching from the right, if we're looking at values of the function just to the right of -1, and we look at a slope of a line there, that's going to be a large negative slope. And in fact, the closer to -1 that we get, the larger the negative slope is. So the right-handed limit is actually approaching -infinity, where the left-handed limit in this particular example is approaching +1. So this limit here does not exist on both sides. It's different on both sides, so it doesn't exist as a two-sided limit. So the derivative does not exist at -1. All right. Now, this is going to be the case anytime we have a jump discontinuity. So if we have a jump discontinuity, what's going to happen is we're going to, from this point to the jump, the branch on the jump, we're going to get a vertical line, or at least approach a vertical line, and it's not going to be differentiable. Okay, so I'm going to start a list over here. A function is not going to be differentiable at jump discontinuity. Okay, let's move on to the removable discontinuity. So at x equals 0, so if we say c is 0, let me use a different color here. So at c equals 0, c is 0, f of c is going to be 3. And if we look at the left-sided limit, the values of the function close to 0 on the left, if we draw lines here, we're looking at the slope of that secant line, it's actually going to approach infinity from the left. So our left-handed limit's going to approach infinity. From the right, we're going to be approaching slopes of negative infinity. And so that means that not only do the one-sided limits not exist, but then the two-sided limit is also not going to exist. So this happens here because the value of the function at this jump discontinuity is different than the values of the function around the discontinuity. So I said jump here, I meant removable. So we're going to have the same problem at removable discontinuities. And actually, if we just remove 3 from the domain of the function, so let's say it wasn't defined there at 3, now all of a sudden, when we say c equals 0, f of c does not exist. And if we're trying to find this limit where f of c doesn't exist, then the limit doesn't exist. So whether or not on a removable discontinuity the function exists at that point, as long as it's a removable discontinuity, this limit is not going to exist and the function is not differentiable. This actually tells us that if f of c is not in the domain of the function, then this limit cannot be computed and the limit doesn't exist. So it's a function is not going to be differentiable anywhere that any x value not in the domain of the function. Sorry for the sloppy handwriting there. Okay, we don't have any other discontinuities here, but we do have a couple other places that we want to investigate a little bit here. So the next place I want to look is at this corner right here. So this is a corner or a cusp in the graph. And so if we look at what's happening when c equals 1, so that means that we're putting 1 in here and f of c is going to be 4. If we look at the two-sided limits again, I don't know exactly what the slopes are going to be here, but as we approach with points from the left, it looks like we're getting slopes that are positive 4, maybe some positive value. And if we approach with points slightly to the right, we're getting slopes that are negative. So regardless of what those one-sided limits are, we know one of them's positive and one of them's negative, so they can't possibly be equal to each other. So at this corner right here, since the slope approaching from the left is different from the slope approaching from the right, that means that the two-sided limit doesn't exist because the one-sided limits are different. So we're also going to have functions that are not differentiable at corners or cusps. These are going to happen often in piecewise functions, so that's why it happened here. We're also going to see corners or cusps in absolute value functions. And remember, when we're dealing with absolute value functions in calculus, the first thing we're going to do is turn it into a piecewise function so that we can investigate situations like this. There's one other one here that's not very obvious, but if we look at what's happening here at x equals 2, we're actually going to run into trouble here also. So when c equals 2 and we approach from, say, the left side, as this point right here gets closer and closer and closer to the point at 2, 3, we're going to get slopes that are steeper and steeper and steeper and approaching infinity. So what we have here in this graph is actually a vertical tangent, and the slope of a vertical line is undefined. So just thinking of the derivative as the slope of a tangent line, that derivative is undefined. If we think of it in terms of this limit, remember when we have a limit that is equal to infinity, it can't actually equal infinity. It's a limit that we say does not exist, but we use infinity to be a little bit more descriptive about why it doesn't exist. So at a vertical tangent, we're also going to have functions that are not differentiable. So, big idea here. We need to know when a function is not going to be differentiable, and we need to know how to look for those things. If we're given the graph of a function, then we can look for these things in the graph of a function. Essentially, we want to look for any kind of discontinuity, because any kind of discontinuity is going to give us trouble with this limit right here. The other things that we want to look for are corners or cusps or vertical tangents. All of these things are going to cause a function to not be differentiable. I also want to mention while we're here that a function can have a one-sided derivative, especially if we're looking at an endpoint. We might say that the derivative exists at this point because the one-sided derivative exists. So if we say c equals 3, we would only really look at 3 from the left side because 3 from the right side is not in the domain of the function. So we might look at one-sided derivatives with functions, and a question involving that would be specific. If I just said, is this function differentiable at x equals 3, that would imply a two-sided derivative, and we would say no. But if we say, is it differentiable to the left of 3, then we might say yes. Okay, so this is a really big idea for this class. If a function is not continuous at a point, then it is not differentiable at that point. So that includes any points that are not in the domain of a function. If a function is not continuous, then it is not differentiable. It's really important that we understand that the converse is not true. So the converse is if we flip the if and then parts, we cannot say that if a function is not differentiable, then it's not continuous. So we have two examples here at x equals 1 and x equals 2, where the function is continuous, but it's not differentiable. All right, so we need to be careful about that. This right here, though, is a big idea. You need to know that if a function has a discontinuity, then it's also not differentiable at that point.